Hello everyone. Today I would like to discuss on the universal gate, and as we have discussed in the previous class, we have many logic gates. For example, we have the basic gates as OR, we have AND, we have NOT. Okay, we have OR gate, we have say AND gate, we have NOT gate, then we have the NAND gate, right? We have NAND gate, then we have the NOR gate, then we have the XOR, or in other words we call it exclusive OR and exclusive NOR, right? So these are the different types of logic gates. So we have the OR gate, AND gate, NOT, NAND, NOR, XOR, XNOR. So these are the different types of logic gates, and the first three, that is OR, AND, and NOT, they are known as the basic gates, right? So they are known as the basic gates. So you can implement any of the Boolean function in the digital system by simply using the AND, OR, and NOT gate. That is the combination of these three gates, which is known as the basic gates. You can implement any of the Boolean function in the digital system. But today I would like to discuss on the NAND and NOR gate. So out of all these gates which we have in the digital system, NAND and NOR gate are known as the universal gates. So what is the reason behind that is that if you want to, for example, if you want to implement any of the Boolean function in the digital system, you can combine this tree, right? You can combine this tree to implement that. But if you have to use the universal gates, you can only using the NAND gate to implement any of the Boolean function in the digital system, or by simply using only NOR gate you can implement any of the Boolean function in the digital system. That is why NAND and NOR gate are known as the universal gate. Alright, so let me discuss about NAND gate for today. So by using only one gate, right, by using only one gate, that is by using only NAND gate, I can implement this. Okay, I can implement this to implement the NOT gate, or using only NAND gate I can implement the OR gate, NAND gate, I can implement the AND gate. So we don't need to combine any of the other logic gates, but we only use the NAND gate. For example, if you remember, we have discussed in the class that the NOT gate, it is given in this, okay, NOT gate is given in this symbol, right? So NOT gate, if you remember, it is given in this symbol. We have one input and we have one output. Now for example, if you say the input, okay, as A and the output as Y, which is equal to A prime, right? So if the input is 0, the output is 1, and again if the input, if the value of A is 1, the output is 0. That is the logic of the NAND gate. So let us see here. we can implement the NOT gate by using the NAND gate. So NAND gate, you remember, we have the combination of AND and NOT, right? So this is the AND gate, and we have the NOT gate, and obviously we have the output as Y, right? So I will use only NAND gate to implement the NOT gate. So what I have to do, I know that NOT gate has only one input, any value which you want to write here. For example, you can write X, you can write Y, you can write A, whatever you want to write the label of the input, and we have the output, right? So in case if you want to implement the NAND gate, okay, implement the NAND gate to NOT gate, I will write down this way. So we know that the AND and OR gate can have 2 or more inputs, but NOT gate has only one input. If you remember, I have mentioned that in the previous class. The NOT gate has only one input and have one output, but the OR and AND gate can have 2 or more inputs and have only one output. So in this case, I wish to implement the NAND gate to OR gate to NOT gate, so therefore I will write down this way, right? So which means if I give A here, so if the value of A is 0, so it will transfer to this line. I will, in this I will get as 0, and in this one also I'll get as 0. So which means when A is equal to 0, both of the inputs of the NAND gate is equal to 0. So what is the output of that? If we know that the truth table of NAND gate, if both are 0, it will be, for example, if you talk about the AND gate, all right, if you talk about the AND gate, if A and B, right, if A and B, if both of them are 0, then the output is 0. If both of them are 1, the output is 1. But in this case we have the NOT gate, so therefore if A and B are 1, then the output is 0, not 0, which is equal to 1. So therefore if A is equal to 0, then I will get the output as 1, okay, which is A prime. I hope you understand that. And if the value of A is equal to 1, I will get this input as 1 and this input as 1. So in this case, if you look here, I will get one input, which is A. So this A will connect to 2 inputs of the AND gate, because the AND gate and OR gate can have 2 or more. All right, that is why I have the input as 1, and then before I connect to the NAND gate, I will split that into 2 inputs. So if A is 1, both of the inputs are 1. If A is 0, both of the inputs are 0. So if A is equal to 1, so if you consider of AND gate, if A and B are 1, okay, if A and B are 1, then the output is 1. If you remember the truth table, okay, so before you understand this, if you are a little bit confused with this, please go back to the AND and OR gate. All right, so if A and B are 1, the output is 1. But in this case, this is the NAND gate. So NAND gate is a combination of AND and NOT. So if I keep NOT here, then this should be 0, right? So if the value of A is 1, so both of them are 1, then the output is 0. So that is how we implement the NAND to NOT gate. I hope you understand this. Or in other words, you will draw this as this one. If you are a little bit confused with this, you can draw it this way, doesn't matter. Okay, so I have this NAND gate. I have the output as Y, then I have two inputs. Alright, I have two inputs. Let's say this is A, this is also A, and if you remember in one of the postulate, it mentioned that x dot x, which is equal to x. If both of the input, if I have two inputs which is the same inputs, right, I have two inputs here and both of the inputs are same, like x and x, so x dot x, I can simply have only one x. This is one of the postulate that we have discussed in the previous class. So in case if you are confused with this, then think this way. If I have two inputs and the inputs are labeled with the same label, A and A, so if A is 0 and A is 0 here, then the output is 1. If you think of, again, if you think of NAND, if 0 0, right, if A is 0 and A is 0, then the output of AND is 0. But we have not, that's why this is equal to 1. I hope you remember. And if A is equal to 1 and A is equal to 1, okay, then I have the output as 0. Okay, that is the truth table of the NOT gate. Right, if A is equal to 0, then the output A prime should be 1, and if A is equal to 1, the output is 0. So if you don't remember, if you didn't understand this, let me demonstrate with the help of one of the software which I have installed in my laptop. All right, so first let me drag this. Right, this is the NOT gate, and then I have the input here, I have the output. All right, then I'll connect this input to the NOT gate, then I'll connect the NOT gate to the output. Right, let me just bring it a little bit down. Okay, so by default, okay, the NOT gate by default, if say this is A, if A is equal to 0, the output is 1. Now if the value of A is 1, the output is 0. So using the NAND gate, I will implement the NAND gate to get the NOT gate. So like I have drawn in the whiteboard, in this whiteboard, I will take this and just draw and drag it in this software. Right, so if you go on these gates, I will get NAND gate. Right, I'll get NAND gate. I will take this and bring it here. Right, so I will have the input. For example, I can do this. I will draw first the input here like that. I will draw the output here. Okay, I'll drag this, connect to the output. Now for example, if I take this like that, right, draw like that, so from one input I'll connect to the NAND gate like I have drawn in the whiteboard. Right, so which means if this is A, if the value of A is 0, I'll get 0 in this line, I'll get 0 in this line. Why I did this? Because the AND and NOR gate will have 2 or more inputs, remember that. So if you look at this, I will demonstrate this. Okay, if the value of A here is 0, I'll get the output as 1. If I get the value of A, for example, I can label this as A, then I'll get the output as 1, so which is the same thing, right? I'll get the output as 1 1, and I will get the input as 0 0. If I change this to 1, I'll get the output as 0. If I change this to 1, I'll get the output as 0. Another one, let me just go back to this NAND gate. Okay, I'll do it here. I will take the input, place it here. Okay, I'll place this one, I'll keep it here. Then I will draw the output right here. I'll connect this to the output. Now I'll connect this to this, I'll connect this to the NAND gate. See, which is the same. All right, so in this case I can label this A and A. Why I do that? Because when you look at the NOT gate, I have only one output, which is named as A. So you can place your A and B, but you'll get the same thing as the NOT gate. So to make it similar with the NOT gate, I will simply name this or label this as A, right? And this is so as A. So which means in this case, both of the inputs are labeled as A, so which is the same input. So let me again demonstrate this. If A is equal to 0 0, the output is 1. If A is equal to 0, the output is 1. If A is equal to 0, the output is 1. If A is equal to 1, the output is 0. So why is it same? So in this case, if I say same input, so if I keep A as 1, this should be so 1. That is how we call it the same inputs. So in this case, I'll keep it as 1. You will see the output as 0 0 and 0. So this is how we implement the NAND gate. Okay, using the NAND gate we can implement the NOT gate. All right, so similarly I will implement using the NAND gate to get the OR gate. For example, I'm in the NAND gate first. Okay, I will first implement the using the NAND gate to implement the AND gate. So if I take the AND gate, okay, if I take the AND gate, I have two inputs. You can have two or more. So in my case, I will just need two inputs. Okay, you can label it A, B or X, Y, whatever you wish to. I will connect this to this one. I'll connect this and connect to the AND gate. Connect this to the AND gate. So in this case, if the value of A and B is 0 0, the output is 0. If the value of one of the input is 1, still it is 0. If both of the inputs are 1, the output is 1. So let us use the NAND gate to implement the AND gate. So what I have to do is that I will drag one NAND gate here, another NAND gate. Okay, this is how we implement the AND gate using the NAND gate. So in this case, let me take this. I will have exactly the same as the AND gate. I will have two inputs, right? A and B or X and Y, whatever you wish to label it. I'll connect this. Now, okay, now let me do it this way, like that, right? Why? Because this is very similar with this one, right? From one input we split into two inputs, because again AND, OR, NAND, NOR and so on, it can have two or more inputs except the NOT gate, right? So I'll have the output, this one, like that. So to implement the AND gate using the NAND gate, you have to have two of the NAND gate, right? You have to have two of the NAND gate to get the AND gate. Now for example, if I click this, if I click this value as 1 and this value as 1, the output of this and the output of this is the same, right? So if I change this to 1, I'll get 0. If I change this to 1, I'll get 0. If both of them are 0, I'll get 0. If one of them is 1, still it is 0. So everything which you see in this, when you apply on this, it will be the same thing when you apply the input for this circuit. So in that case, two of the NAND gates can form the AND gate. So if both of them are 1, the output is 1. If both of them are 1, the output is 1. I hope you understand that. So see, I have the AND gate, the NAND gate, right? I have the NAND gate. I have the input as A and B. So this is A and this is B. So I will get the output here as A dot B, because we have the AND gate and then we apply the NOT gate, so both of them are prime or complement. So again, if I apply this, I will complement this again, right? I'll complement this again using the NAND gate again, right? Using the NAND gate again. What I'll get this one, I'll get this one, A dot B, whole thing complement, again complement, because of this. See, from this we got A dot B complement because of the NOT gate. Again, when I apply this on the NAND gate again, I'll get this and this, and then again this NOT gate. Okay, the whole thing NOT gate. Okay, so you can even write it this way: A dot B, this is prime, this is prime, A dot B, this is prime, this is prime, and then whole thing prime. Okay, you can write it this way or you can write it this way. So now when you apply De Morgan's law from one of the postulates that we have discussed in the first class of this unit 2, if you apply this, so this prime and prime, it got cancelled. I'll get A, and then this prime and this dot, no, not that way, it should be this way, right? Okay, it should be like this, right? So I'll get this, I'll apply De Morgan's law of this, A dot B complement, which I use this one, right? Use this one. So what I'll get here, I'll get A prime, this one and this one, I get A prime, and then this one and this one, this dot change to R, right? So I'll get P prime. I hope you understand that. So now again I will apply this prime, so whole thing prime again, right? Whole thing prime again, which I will get as prime and prime cancel, I'll get A, right? And then prime and OR operator now will change to dot operator again, and prime and prime get cancelled again, so finally I'll get it as A P, which is the output of the AND gate. So if you remember the AND gate, right? If you remember the AND gate, if I have A and B as the inputs, the output Y, which is equal to A dot B, right? So I can apply, or I can implement using a NAND gate to get the AND gate. That is why NAND gate is known as the universal gate. And finally, okay, finally I will implement using NAND gate to get the OR gate. Okay, this is very simple. It's very clear for you also. When we demonstrate this, you'll get exactly the same output when you apply the input for this and for this also, using the NAND gate to implement the AND, using the NAND gate to implement the NOT, and finally let me just draw the OR gate. Right, OR gate can have 2 or more inputs, but in my case I will have only 2 inputs. And yes, we know that logic gates can have more or two or more inputs and can have only 1 output. Okay, that is the fundamental of logic gates. So I will connect this to this, and I connect this to this. So to implement using the NAND gate to get the OR gate, what I have to do, I have to have 3 of the NAND gate. Remember, I have to get 3 of the NAND gate. So everything here deals with logic, right? I'll connect this with this. Okay, so I'll connect this, bring it down, connect this, take it up, and finally I'll connect this to this one, this to this one, like that. Then in this case, either I will choose this or I will choose this. It doesn't matter. It'll be the same. Either I'll choose this, I'll have 2 inputs, but 2 inputs should be the same inputs, which means if I have A1 here, the other A should be 1. If this is 0, this 1 also should be 0. It cannot be this is 1, this is 0, because we have the same inputs. So either I'll use this or I will use this. Okay, so let me use this, because we know that this and this is the same. So I will choose 1 input for this and 1 input for this, right? I cannot connect it just like that, okay, because we know that OR and NAND NOR can have 2 or more inputs. That is why I'll make sure that I have 2 inputs for this one and connect it to this gate, like that, right? Similarly with this, I'll connect like that. All right, so you will see, okay, you'll see if the value of one of both of the inputs are 0, the output is 0. In this case, 0 0, and we got the output as 0. You can label this A and B, and this is A and B. It's the same thing, right? A and B, A and B. Now if I change one of the inputs, say A is equal to 1, I'll get the output as 1. If I change this to 1, I'll get the output as 1. Alright, I'll get the output as 1. If I change this to 1, I'll get the output still 1. Change this to 1, I'll get the output as 1. So whatever you apply the input for OR gate, also for this one, you'll get the same output. Now I'll change this to 0, still I'll get the output as 1. I'll change this to 0, still I'll get the output as 1. So which means these gates and this gate is the same. Okay, that is how we implement using the NAND gate to form the OR gate. So using the NAND gate to implement the OR gate, using the NAND gate to implement the AND gate, using the NAND gate to implement the NOT gate, right? So that is why NAND gate is known as the universal gates. So in case of NOT gate, we have only 1 of the NAND gate. If you have to implement the AND gate, you need to have 2 of the NAND gates. In case if you want to implement the OR gate, you need to have 3 of the NAND gates. So remember, 1 to 1, 2 to 1, that is NAND to AND, and then 3 to 1, that is NAND to OR. I hope you understand, and in case if you have any doubts with this, please comment in the comment section below. In the next class, I will discuss using the NOR gate to implement the 3 basic logic gates. That is why NAND and NOR are known as the universal gates.